Have you ever really stopped to think about how language works? I mean, not the grammar rules from school, but the deep, computational engine that's humming away in your head. Today, we're going to dig into a really elegant idea that flips grammar on its head. What if words aren't just static labels? What if they're actually active functions? So let's start with a classic line. Time flies like an arrow. Seems pretty simple, right? Well, for a computer, and honestly, for us too, if we really pick it apart, this sentence is just a minefield of potential meaning. Your brain, of course, just instantly gets it. Time moves fast. But grammatically, that second interpretation is totally possible. There's this famous story, probably not true, but who cares, about an early translation machine that got this hilariously wrong. It thought time flies were a specific kind of insect that really liked arrows. And that highlights a massive challenge. And that is the absolute core question. Language is just swimming in ambiguity. A single sentence can have hundreds, maybe even thousands of different grammatical structures. So how do we sort through all that chaos so effortlessly? Well, to figure that out, we need a theory of grammar. To really appreciate the solution, we first have to understand just how deep the problem goes. You see, grammar is constantly solving these incredibly tricky puzzles behind the scenes. So check out these two sentences. I gave Ike a bike. Super straightforward, right? The words that belong together are sitting right next to each other. But then you get something like the sentence on the right. The word violin is meaningfully connected to the word upon. But look at them. They're miles apart in the sentence. This crazy puzzle is called discontinuity, and it is a huge headache for any theory of grammar. So how have linguists usually tried to fix this? Well, the most popular approach for a long time has involved an idea called movement. Okay, so the basic idea here is that words like which violin don't actually start at the beginning of the sentence. No, they start somewhere else, like maybe right after the word upon, and then they get moved or displaced all the way to the front. It's like the grammar has to do this complex shuffle, moving pieces all over the board and leaving behind these little invisible traces of where they used to be. Now, this is a pretty powerful idea for sure, but it comes with a lot of baggage. You end up with this huge, growing list of rules and special conditions just to control what can move where. It gets incredibly complicated. And it raises this one really big question. How on earth could a child learn a system this complex, with all these hidden movements and abstract rules, just from listening to adults talk? It seems unlikely. And this brings us to a totally different and frankly much simpler way of looking at things. Combinatory categorical grammar, or CCG. This right here is the aha moment of CCG. Just forget about words as these passive blocks. Instead, I want you to think of every single word as a tiny little program, or a function. And each function knows exactly what it needs, what kind of ingredients it's looking for, to build something meaningful. So in this system, every word has a special entry in the dictionary, a categorical lexicon, that basically defines its job. Let's take the verb seize. Its category looks a little bit like code, S/NP/NP. The slashes tell you everything you need to know. That //NP means it's hungry for a noun phrase, the object, on its right. Once it finds one, say a fish, it transforms into a new function, S/NP. Now, the backward slash says it's looking for another noun phrase, the subject, but this time on its left. When it gets that, say the word I, boom, it finally becomes a complete sentence, or S. You know, the easiest way to think about this is with Legos. A word like seize is a very specific kind of Lego brick. It's got a peg on its right side, shaped just right for an object, and a hole on its left side, designed perfectly for a subject. Grammar suddenly isn't about a bunch of complicated rules. It's just about clicking these bricks together in the only way they'll possibly fit. It's that simple. All right, so let's see this whole Lego brick idea in action, because it turns out that this incredibly simple concept can solve some of the most complex puzzles in grammar, all without any of that messy movement stuff. Get a load of this sentence. I admire and you detest sincerity. Traditional grammar really trips over this one, because I admire isn't a standard, complete thought. But in CCG, It's a piece of cake. The words I admire just click together and they form a perfectly valid new function, a new building block that's just waiting for an object. Then, you detest does the exact same thing. And because they're now the same type of function, the word and can combine them into one big function that then takes sincerity as its shared object. And just like that, puzzle solved. There's no movement, no hidden copies, no secret structures. Everything is built right there on the surface just by combining adjacent pieces. Things that other theories would call grammatically illegal are perfectly valid building blocks in CCG. It is just an incredibly elegant solution. So this is all very neat, but why does it matter? Well, it turns out this elegance has huge implications for how we think about the human mind, about artificial intelligence, and about language itself. And this right here shows one of the biggest wins for CCG. It gives us a really believable model for how kids learn language. What you're seeing is a computer model that's learning verbs using these CCG principles. And what's amazing is that it works even when the input is messy and full of distracting junk. You know, exactly like the world a toddler hears. It suggests that a child's brain could be running a very similar, simple, combinatory program. This elegance is also a huge deal for computers. In the world of AI, there's a technique based on CCG called super tagging. Instead of just labeling a word as a plain old verb, the computer assigns it its full functional category, its complete job description. Giving the AI that much richer information dramatically boosts its ability to accurately understand what we're saying. So what about all the different languages in the world? I mean, English is subject-verb-object. Japanese is subject-object-verb. Welsh is verb-subject-object. A movement theory might need completely different deep-down rules for each one. But CCG, it handles this so easily. The only thing you have to change is the direction of the slashes in the dictionary. A Japanese verb might just say, find your object on the left. But the core logic, the simple act of combination, stays exactly the same. And this leads to some incredibly powerful, testable predictions. For a simple 4-part phrase, there are 24 possible ways you could order the words. CCG predicts that exactly 2 of those combinations are impossible. Not just in English, but in any human language. That's not just a description. That is a bold, scientific claim that you could actually go out and try to prove wrong. So let's just wrap this up. What have we learned? 1, words are active functions, not passive tags. 2, all the complexity of grammar can emerge from just a few simple local combination rules. 3, this gives us a fantastic model for how language works in both our brains and in our machines. And, maybe most importantly, all the really hard work of grammar is packed into the lexicon, the dictionary of words, not into a bunch of abstract rules. And really, this is the ultimate punchline. All of those complex ideas, movement, displacement, raising, they can all be boiled down to one single, simple, local operation, just combining 2 things that are right next to each other. It's a profound simplification of what grammar truly is, which leaves us with a final, pretty mind-bending thought. If language, one of the most complex things we do, can be built from such simple and elegant first principles, what does that suggest about the code that's running in our own minds? It suggests the operating system in our brains might just be far more elegant than we ever dared to imagine.